Hello, Michael Smart here again. In this part of our module, we're going to be talking about Scramjet performance analysis. And what I mean by that is, how do we calculate how much thrust a scramjet will generate? Just like any propulsion system, thrust is the key, and so that's what this module will be about. If we plan to use a scramjet engine as a propulsion device, we must have a means of calculating how much thrust it can generate. Here's the schematic of a scramjet-powered vehicle. It's travelling to the left with velocity v, which is hypersonic, and in doing so generates a shock wave at its leading edge. Now, a scramjet-powered vehicle is made up of a couple of different parts. There's the vehicle airframe itself, there's the internal flow path, which captures the air and is part of the engine, and then there's the external cowl, which is sort of the external surfaces of the engine. Now, what are the forces on a scramjet-powered vehicle? Now, externally, we have drag forces. So there will be a drag force, dV, which is basically the drag of the vehicle that your scramjet engine is trying to propel. For many reasons, we also like to differentiate the drag on the external part of the engine, as this aspect of the engine design is determined by the propulsion engineer, and so dE is the external drag of the engine. Now, what about internal forces? Now, as we've mentioned, the scramjet engine generates thrust by capturing air, and here I've indicated a stream tube of air that is passing through our engine. And as one can see, the flow of the air is affected by the shock wave off the front of the vehicle. So the scramjet engine will capture a certain amount of airflow, and we'll indicate this with m dot, and we'll call this m dot air. In order to generate thrust, we also must inject fuel into the combustor region of our scramjet, and then the fuel and the air mix together, burn to produce combustion products, and all these products must exit our scramjet engine. Now, in doing this process, the internal surfaces of our scramjet will encounter both pressure loads, as I'm indicating here, which are always normal to the surface of our scramjet, but we also have shear loads due to viscous effects of the airflow through the engine. Now, it's actually the sum of all these forces that on the inside of the engine that determine the thrust that the engine supplies to the vehicle in order for it to accelerate. And so if this internal thrust is greater than both the vehicle drag and the external drag, then we'll be propelling our vehicle forward. Now, there are two possible methods which can be used to calculate this internal thrust T. As I just drew, it is possible to calculate these directly, or this force directly, by adding up all the pressure loads and the shear force loads and all the engine components. Now, I've drawn a very simplified schematic of a scramjet. A real vehicle is much more complex than that. In order to use this direct method to calculate thrust, you have to go through a very complex process of calculations, which is really not desirable. Now, luckily for us, an alternative method is to apply Newton's second law to what's called a control volume, which is placed around the surface of the scramjet flow path. Now, this is an indirect method, but it ends up being considerably simpler than trying to do detailed calculations of every small component in your scramjet engine. And this is the analysis that's used by all propulsion engineers, not just for scramjet engines, and it's called stream thrust analysis. And that's the analysis that we'll be using in this course to calculate the thrust of our scramjet. So here again is the schematic of our scramjet. We have the airflow coming in, fuel being injected, burning with the air, and then our combustion products leaving the engine. In the last slide, I mentioned a thing called a control volume. This is simply a box we can draw with any shape we want and then apply Newton's second law to it. Now in our case, we want to choose this box to be around the inside of our scramjet, and we do this because it helps us to calculate the thrust in the easiest way. So here I've brought up a picture of a typical control volume for a scramjet. So the front part of the control volume is normal to the airflow coming in. The bottom surface is parallel with the vehicle flight upstream of the forebody shock or any disturbance from the engine or from the vehicle, and then downstream of that follows the line of the captured air. Now on the internal surfaces of the flow path, the control volume is on the surfaces of the flow path and sticks to whatever shape that might be. Now at the back end of the scramjet, because of the higher pressure that's generated by the combustion products, we can have some expansion of the plume, and so the back part of our control volume should always follow that, and then the final closing surface we have at the rear of the vehicle, which is typically normal once again to the flight direction. Now applying Newton's second law to our control volume allows us to equate forces on the surface of the control volume with the flux of momentum due to the airflow that passes through the control volume. But in order to calculate these forces, we need to define a few extra things. First of all, at the inflow, we want to define the pressure of the inflow, which is the atmospheric pressure where the vehicle is flying, as P in. And we also wanted to define V in, which is essentially the velocity of the air passing into the control volume, which is in fact the flight velocity. We also wanted to define the area at the front of our control volume, A in. Similarly, we need the properties of the combustion products as they exit the control volume. So the pressure of the combustion products is P out, the velocity of those products is V out, and then the area of the plume is A out. And all these extra parameters we've introduced will come into our equations for calculating thrust. Now all the forces that are applied to the scramjet vehicle will have both components in the streamwise direction, so parallel with the flight velocity, but also normal to that. Now here we're most interested in forces parallel with the flight direction, in particular the thrust of our scramjet, and so we'll align the x-axis with the flight direction. Now in other analyses we may be interested in the lift forces generated by the engine or the vehicle itself, and then we would do similar calculations in the direction normal to flight. Okay, so now what are the streamwise forces on our control volume? Now the first forces are from the entrance to our control volume and the axial force of the inflow pressure times the inflow area. And similarly, there is another force at the exit of the control volume, which is P out times A out. Many of the other surfaces of the control volume are the ones we are interested in that contribute to our thrust, and I'm drawing on some of them here. So all the surfaces where the control volume is in fact touching the inside of our scramjet flow path, all those forces will contribute to the thrust that the scramjet engine supplies to the vehicle. Interestingly, that thrust is equal and opposite to the thrust force, or the reaction force to the thrust, that the vehicle applies on our control volume. And since we're doing the analysis on the control volume, we actually are interested in a force in the other direction, which is our reaction to the thrust. Okay, so we've covered a lot of the surface of our control volume, particularly with the inflow, the outflow, and then everything that's touching the flow path. However, there are a few extra little bits which we do need to worry about in order to calculate all the forces on our control volume. So you will notice that I've labelled the bottom surface of the control volume A, B, C, D, and E. And so I've done so that we can break up these parts of the control volume into some different terms. Now if we start with the first term between A and B, where the control volume is actually aligned with the x-axis, and the forces that contribute to the control volume are the integral from A to B of the pressure times the component of the area that's normal to the x-axis. And because this line is parallel with the x-axis, that term is 0. So that's a nice one. Now, however, from B to C, we can notice that the line on the edge of the control volume is not now aligned with the x-axis. And this is because the flow has been turned by the four-body shock. Now this term, similarly, is the pressure times the component of the area normal to the x-axis, is not 0 unless the engine has full capture. And this term is known as spillage drag, and we will indicate it as F spill. So there is actually a force which is in the x direction associated with that part of our control volume. Okay, now all other surfaces of the control volume have been taken care of except between D and E in the plume area. And so there's a similar integral, P dAx, so pressure times the component of area normal to the streamwise direction. And if the plume is not perfectly matched with the external flow, we get another force here called the plume drag. And we'll indicate that with F plume. And so we have another complicating force. Now, historically, these two terms have been combined to be called the additive drag. Now, they are not forces or drags in a real sense. What they are terms that are a consequence of the fact that we've used our control volume. And in order to calculate our thrust using this method, we need to be able to evaluate these two terms, or the combination of these two terms, which is the additive drag. Going now to the right-hand side of the equation, which is associated with the momentum flux of the airflow crossing the control volume, we have fluxes due to the inflow of the air and also due to the inflow of the fuel into the control volume. Now, in the formulation of Newton's second law for a control volume, fluxes, inflow fluxes, are considered negative. Now, in addition to those, we also have the flux of air and combustion products out of the control volume, and that is shown here. So these are our two fluxes that we need to include in our Newton's second law. Now, for simplicity here, we're actually going to drop the flux due to the fuel, or essentially assume that it's small, and equate it to 0. So if we now equate the left and right hand sides, we get all the forces on the left hand side, including the thrust, which is what we're trying to find out, and all the fluxes on the right hand side. Now, if we rearrange this equation, we leave the thrust T on the left hand side, because that's what we're trying to find, and we've arranged all the terms associated with the outflow together, and then all the terms, and inside the red brackets, and then all the terms associated with the inflow together as well, and then we have the additive drag as our extra term. Now, you will notice that each of these terms in the red brackets are in the form of a pressure times an area plus a mass flow rate times a velocity. All these terms have units of force, and together they are known as the stream thrust. Now, the stream thrust, and we'll use F to indicate that, is defined as pressure times area plus m dot v in a particular stream of some kind. And so, instead of using our complete equation here, we will actually use F to indicate the stream thrust. And so the first term in the red brackets we now will call F out, so the stream thrust associated with the outflow. The second term is F in, and so it's the stream thrust associated with the inflow. And then, of course, we have our additive drag term. And now we have a very simple equation to calculate the thrust of our scramjet. So how do we calculate all these terms? So first of all, the additive drag. Now, this term is associated with, if you remember, the shape of the control volume, essentially, both on the inflow side and the outflow side. It typically depends strongly on flight Mach number. When an engine is actually close to its design point, the additive drag can be very, very small. However, when it's not close to its design point and it spills lots of air, the additive drag can be a term that's very important to calculate. Now, unfortunately, it's never easy to do this, and so in simplified designs of scramjets, we typically use rules of thumb for the additive drag, but if we really want to know, we have to do quite a complicated computational analysis. A second term is the stream thrust of the inflow. Now, if you remember, a lot of the terms in this were associated with the flight velocity, the atmospheric pressure. The only real term that we don't know is the free stream capture area, A in. However, if we know the amount of air that's flying through our engine, we can very easily calculate this. So this term is actually quite easy to calculate. Now, the third term, and actually the most important, is the stream thrust of the flow that's passing out of the engine. And this is the term that really dictates whether our scramjet will generate positive net thrust or whether our T will be negative. And in order to determine both the velocity and the complete stream thrust of the flow going out of the engine, we really need to follow the air and the fuel through the entire engine. And this process is quite complicated, and it's actually going to be the basis of the analysis that we're going to start right now.